Hello team, it is I, Willow Pichardo, at 12:14 in the morning, bringing you a wonderful, hopefully wonderful, LTSpice video. This is the first video of what I believe is going to be a series on LTSpice. This is going to be strictly an introductory video, so you should be able to watch this during your first lab. Maybe after first lecture, maybe after your first lab. And you should definitely play around and experiment with LTSpice after watching this video, just to get a feel for it. Every time you are building a block for your circuit, you should simulate it before you build it. And when you're making changes, you should simulate the changes before building the changes. The simulation is going to show you what your circuit is expected to behave like, right? So if your simulation works, you need to make sure that your hardware follows the simulation. This is a very powerful simulation tool. So if you get the simulation right, you can get the hardware right. All right. So without further ado, let me get that out of the way that I'm using Windows. I don't have a Mac. I wanted to do a Mac video, but I don't have a Mac. So we're going to do Windows. At the top, we have this toolbar. It has the settings icon. It has new schematic and open and save and all these other things. First thing we're going to do is we're going to make a voltage source. It's kind of like our battery, right? Or our power supply that we're using in our lab. And it's right here. It also says that you can click V. So if we click V, we get a little voltage source. You can use the scroll wheel in and out to zoom in and out. Okay. And now I'm going to left click and I'm going to place the voltage source. And then it changes different versions. You can place as many as you want. I am going to hit escape. All right, escape. So now, for the next part of our very complicated circuit, we're going to add a resistor. Boom, I just summoned it out of nowhere. How did I do that? Well, I used R for resistor. The resistor is found at the top here, but you can click R in order to get your resistor, right? So now we have a voltage source, and we have a resistor. And so we're going to connect these with wires. And we can get a wire up here, or we can click W. It's very nice, the letters that are associated with the keybinds. And so now we want to connect these squares using the wires. So as you notice, there's a blue square, and this indicates that it's unconnected to anything. So we're going to click on it, and that's going to start a wire. And then we're going to click on it, and clicking places the wire. And you can place them at 90-degree angles, right? And so here's our circuit. You can left click on the background to drag and move yourself around. Okay? So we have a voltage source, we have a resistor, and you know what? I'm going to add another resistor. A fancy thing you can do is you can place the resistor in the middle of the wires and it'll automatically connect it. We want our resistor to go horizontally, right? Not vertically. So now we are going to learn. I should probably learn how to mute my notifications before starting videos. Now we are going to learn how to rotate an object, and we're going to use Control R. Okay? Control R will rotate this object, and now we left click, and it automatically places it in, right? Okay, so now we need to select values for our circuit. So I'm going to consider this to be like a 9-volt battery. So I right-clicked on the voltage source, and you get a menu that says DC value and series resistance. The DC value I'm going to set is 9 volts. Okay? You don't need to worry about series resistance. When we're describing like batteries and stuff, technically they have a series resistance. It could be just like a few ohms. We're not describing that. We're talking about ideal voltage sources. So we're going to say that we're just going to do a voltage, right? For our resistors, let's do just 2 simple resistors. Let's do 2 1,000 ohm resistors in parallel. You could do 1,000. What if you get to 1 million? What if you get to 1 bajillion, right? You can actually type in prefixes automatically. Well, not prefixes, units. So 1, and then we hit K, right? And 1K will register to LTSpice as 1,000. You can do 10K. You can do 1 meg for mega ohm. You could do 1 M for like millifarad. And then you can do 1 U for micro. You can do any units that you desire. Okay? So we're going to do 2 1K ohms in series. And now we need to determine a reference point, because LTSpice is going to simulate this circuit, and it's going to give us voltages around this reference, right? So we need to place a ground. Ground is found up here in the tab, or we can press G. And my advice, especially for moving forward in this course and solving circuits, is I usually place the ground below voltage sources, right? Because if we know that this area right here is ground, this is 0 volts, then we know that the area right above it is 9 volts, right? Okay, so now we have a completed circuit. We have a reference ground. And now we need to simulate our circuit so that we can get actual values out of this, right? So there's a lot of tabs to go through. So what I did was I went up here and I went to .ac. There's many tabs, right? There's transient, AC analysis, DC sweep, noise, DC transfer. Really, we're only going to be focusing on the transient analysis, but it's also important to note the DC operating point. The DC operating point is steady state. There is no changing signals, no AC. And so if you just go to DC operating point and hit OK, it'll give you the text box. You left click to place the text box on the screen. I don't like where it is right now, so I'm going to hit M, and that's going to be allowing me to move the text wherever I want. And now that we have this is called a spice directive because it has a period behind it. LTSpice will read this spice directive and it'll say, okay, we need to calculate an operating point. So now if we hit the play button, right, or do Alt-R, it'll give us a list of all the values it calculated. I don't care. We can instead now click onto different sections of the wires and it'll tell us the voltages at these points, right? Now, ideally, wires have a voltage drop of 0, right? So if we click across, it's the same exact voltage. These are all under ideal conditions. And then if you hover over the component, you can actually see that we're at 4.5 milliamps. It says negative, and the reason why it says negative is the direction of the resistor. If we wanted to change the direction, we can just rotate it. And then if we do this, now it's positive. This symbol looks not really different, right? In this case, it's where it goes down first, is that this is the positive end and this is the negative end. When we're doing the transient, there's an easy kind of symbol that shows you where the current's going. But that's not important for this case. In this case, we can kind of understand that current flows from high to low in potential. So 9 volts to 4.5 volts. We have 4.5 milliamps going to the right. And then 4.5 milliamps going through here. And it just creates a loop. And that's our first simple circuit. If you followed along and you built this, congratulations. You have built your first simple circuit. And we're going to move on to something more complicated. We are now going to use a variable voltage source. Okay, so there's ways you can make variable resistors, and that's more complicated. I think I'm going to do that in a later video, but I think it's worth highlighting what you can do with our voltage source. So I'm going to delete these numbers, not that it's important, and I'm going to delete the spice directive. Okay, I want you to right click on the voltage source. And now we're going to go to the advanced section. There's multiple tabs here, just like the .ac, but we're only going to be looking at pulse and sine. Primarily sine for now. And in sine, we can leave all these blank except for the first 3. The first 3 is really all we care about. DC offset, amplitude, and frequency. I'm going to give it an offset of 0. So it's going to oscillate around 0 volts. If you think of a sine wave, it naturally oscillates around 0, with the amplitude being like whatever, 1 in a standard sine or cosine. Amplitude here, I'll make it 4.5. And then the frequency, let me make it 1 kilohertz. So I'm going to do 1K. So we have created a sine wave. How do we see this sine wave? Well, this now requires us to use the transient analysis. The DC operating point won't work for this because we have AC. We have an alternating current. Our voltage is varying over time. It's a sine wave. So now we need to use this panel. And most people use this panel just for the DC. And there's really not that big of a deal other than the fact that it's a little more computationally excessive, right? So the first box is our stop time. And because we're doing a 1 kilohertz sine wave, I like to make it 0.01, right? You can do the math and see how many cycles that would give you, or you'll literally see the number of cycles. Time to start saving data. I always make this 0. I think you guys should always make it 0. I want to start saving data at the time that the circuit starts. Like, there's no reason to wait a few seconds. And that just makes your math a little weird if you're not starting from 0. And then maximum time step. So think of LTSpice as this guy, right? And this guy, he's calculating the circuit at individual times, right? And if you have a really large time step, he's going to calculate it at 0 seconds, and he's going to calculate it at 0.01 seconds. You're missing all the data in between. And so if you give him a shorter time step, he has to calculate more points, and that'll give you a better image and a more accurate description of how your circuit's behaving. If you give him too small of a time step, he's going to be calculating for decades, right? Trying to get every single point, and then you have too much resolution. You don't really have to worry about this. Most people, aka what I saw from Professor Gockerback, he would do 1e negative 5. So 1 times 10 to the negative 5th. And that's more than enough resolution. And it also results in not lagging. Like, it doesn't take too long to simulate. Start external DC supply voltage at 0. You do not need to turn this on. This is if you want to see what your circuit does at power up, because there's like voltage spikes and things we don't care about. We don't need to turn this on. Stop simulating if steady state is detected. This could optimize your simulation, because if you're just simulating for a long time and it's in steady state, it doesn't need to keep simulating, right? However, you can fix this problem by just like having a reasonable time. So we don't need to turn this on either. And then we don't care about any of this. So you literally fill out the 3 boxes, and there you are. We have our text. Make sure you left click. It needs to be on the screen, right? We should be able to move around, look around, do other things. It needs to be placed on the screen. And now we're going to hit play. And now a graph is going to show up. It's blank. The green play button has shown up again, which means our simulation is complete. And now let's click to see this voltage. Now we see that there are multiple sine waves, right? Or, well, it's one sine wave, and it just oscillates, right? So 0 volts, positive 4.5, negative 4.5. This is where our voltage has gone to, right? So now we can plot another voltage and compare it. So this is our node 2. So this is V node 1. If you look in the bottom left corner, there's V node 1. And if you look in the bottom left corner, this is V node 2, right? If you highlight over it, you can see nodes. If you want to have your nodes be specifically named, you can name your nodes. If you right click and you do label net, or you hit N, I'm going to do voltage source. Okay, I forgot that I can't use a space. That's my bad. Absolutely humiliating. And now we'll throw that on there. And then if we do, I'm going to label this one as in between. And then we run this again. We click on the voltage, click on the voltage. So now our green is V voltage source, and our blue is V in between. And notice how our V voltage source goes from 0 to 4.5 and negative 4.5 as we'd expect. And this circuit is a voltage divider. It divides the voltage in two. So at every point, the blue voltage is half the green voltage, right? And you're not limited to just plotting voltages. You can actually plot currents, and you can plot voltage and current at the same time. You just have to make sure you know how to read the graphs. So if I click on the current for R2, notice how I said, remember with the transient, we have a nice symbol that shows us where the current is going. This is an old style ammeter. It would use the induced magnetic field of the wire to read the current going through the wire. So that's what that symbol is representing, and the arrow shows the direction. So it's saying that the current is going to the right. If we click on it, it's almost directly covering the green one. So if you double click on a source, it'll highlight just that one and get rid of the rest. So now we can see that IR2, so the current going through R2 goes from 0 to just over 2.0 and back down. And oscillates, right? And we could do the same thing here. These are completely in phase with one another, so they just completely overlap, right? So that is some basics with the waveform. Another thing I'd like to show is, I'm going to show these again. Say we only want to look at one waveform, but we only have we have all 10 milliseconds. If you want to zoom in, you can actually drag from one corner to another, and it'll zoom you into that one location. So now you can see in higher resolution the differences between the two, right? If you need to, you can hit Control Z, and it'll literally shift you back to where you started. I think this is a clear enough overview of how to set up a simple circuit, how to view the waveform, how to make a sine wave voltage source. You guys should definitely experiment in LTSpice just to get a good feel for it, because LTSpice is going to be pivotal to making sure that you can accurately design your projects, and it will be significantly helpful in debugging your hardware when that time comes. So good luck. Leave a comment if you have any questions, and yeah, have fun.